In problem number 1, the probability of winning a carnival prize is 1/7. And it says in the problem these are independent events. So it doesn't matter what happened the last 9 times. So the probability of the next win is 1/7 because they are independent events to each other. In problem number 2, a friend takes plastic discs and invites you to select them at random. Half of them are red, half of them are blue. After you take a disc, you replace it. That means these are independent events. So if you repeat this process of taking them 100 discs and you replace them each time, probability stays the same. So the overall proportion of red disc is close to 50%. In problem number 3, we have information about music and gender. So here's the types of music, here's the genders. They want to know which one of these statements are true. So they want to know, are the events mutually exclusive? No, they're not. Because you can like vinyl and you can intersect with male or female. So they are not mutually exclusive. So I'm going to cross off everything that says mutually exclusive. So they want to know if they're independent. So to figure out if prefers vinyl and male are independent, I'm going to calculate the probability of male. So that was 300 males and out of a total of 550. So that's how I got this probability. And then I need to calculate male given that they like vinyl. So I am going to look up vinyl. So vinyl I had a total of 88. And how many males liked vinyl? 48. And notice I got the same probability for both of these events. That means these events are independent. And here is the rule for independence. One can't affect the other. So my answer is B. So problem number 4 is dealing with blood types. O negatives are universal donors. So only 7.2% of the population has O negative. If 10 people appear at random to give blood, what's the probability at least one is a universal donor? That means 1 out of 10, 2 out of 10, 3 out of 10, all the way up to 10 out of 10, because we want at least one. So it's much easier to the complement rule to figure this out. So I want to know the probability of at least one is a universal donor. So I am going to go 1, because the probability has to add up to 1, minus none of them are universal donors. So the probability of one donor, they told me in the problem, so that was 0.072. So I'm going to go 1 minus that probability. That's how I got 0.928. And I want to do this 10 times. So I'm going to go 1 minus 0.928 to the 10th power, because the first one and the second one and the third one and the fourth one, that's why I'm multiplying here. So that's how I got 0.5263. In problem number 5, a die is loaded that means it's not a fair die. So the number 6 comes up 3 times more often than the other numbers. I want to know what's the probability of rolling a 4, 5, or 6. In order to figure this out, I first need to do the sample space. Here's my die, and here's my outcomes. 1, 2, 3, 4, 5, 6. The problem says that 6 has to come up 3 times as often, so I'm going to make that a 3, and make all the other outcomes 1. So then I'm going to make a table of values. The probability of rolling 1 is 1 out of 8, because if 6 comes up 3 times as much, that gives me a total of 8. So here's the rest of my probabilities. So the probability of rolling a 4 is 1/8. Probability of rolling a 5 is 1/8. Probability of rolling a 6 is 3/8, because it's 3 out of 8. That's how I got 5/8. Remember, make a sample space. In problem 6, you have a bag of candy. It has red, green, orange, and blue candies. I am taken without replacement. That means it's dependent. Once I take one candy, the probability is going to change. I have a total of 50 candies. I'm looking at the probability the first candy and the second candy are red. Because I'm looking for red and red, I am going to multiply. First time, there's 20 candies out of 50 that are red. If I take one red candy out, there's 19 out of 49. So that gives me 38 out of 245. So that would be A. In problem number 7, it says event A will occur with a probability of 0.5. Event B will occur with a probability of 0.6. And A and B is 0.1. So we want to know if these probabilities are independent. They are not independent, because if they were, the probability would be exactly the same. One would not affect the other. Are they mutually exclusive? I don't know, because it's not in context. Are they complementary? No, they're not, because they would add up to 1 if they were complementary events. So, choice C, either A or B always occurs. If I say event A or B, I'm going to add them. So, I'm going to add up event A, add up event B, and I am going to subtract the overlap. The overlap is the 0.1. So I got 1, that means this event will always occur, because my probability is 1.0. In problem number 8, the probability that event A occurs is 0.8. Event B occurs given that A has occurred. That's a conditional probability. That's 0.5. I am looking for both events A and B to occur. I said A and B. That means I'm going to multiply them together. So the probability of event A times the probability of event B given that A has occurred is 0.4. If I said A or B, I would be adding these and subtracting the overlap. Question number 9 says 60% of the students have high-speed internet. 30 have mobile computing device. 20% have both. So I want to know the proportion that have neither high speed nor mobile computing. So I am asking, this is an OR question, so I am going to add. So if I find the probability of high speed, I'm going to go 60%, mobile is 30%, minus the overlap. That's 70%. But they want to know that neither have them. So I'm going to use the complementary rule. I'm going to go 1 minus 0.7 is 30%. That's how I got C. Problem number 10. The only way to understand this is to make a tree diagram to calculate the probabilities. So the problem is talking about a certain lie detector given positive readings 10% of the time. so indicating a lie. And 95% of the time when a person's lying. So suppose if we take a sample of 5 people and we want to know the probability of getting no positive readings if all plead innocent and they're telling the truth. So here's the lie detector. If they are guilty, it will find them 95% of the time. That means 5% of the time it won't find them. If they're innocent, 10% of the time will indicate a lie, 90% of the time not a lie. So here's my other branches. Now I need to calculate my probabilities for each branch. So I'm going to go 0.95 times 10%. And I do this for every single branch. So the question says they want to know if the machine's working. So if the person's guilty, it's going to catch them, it's going to indicate 90% of the time, so this is a correct reading. So if the person's innocent and it reads innocent, this is a correct probability. So I am going to add up my correct. So the probability it's a correct reading is 90%. So I want to know the probability that all 5. This one is just for one person, so I'm going to go 0.9 to the 5th power. That's how I got 0.59049, which would be D. In the free response question, we have a simple random survey about political views by age group. We want to know the probability a person is a moderate. So that would be 75 over 255. In question B is a conditional probability because we want to know their ages have to be between 30 and 44. So between 30 and 44, that's a total of 85. So I got 85, given that they're moderates. So that's how I got 30. 30 out of 85. In problem C, they want to know, are these events independent? So when we calculated moderate, we got a little more than 29%. When we calculated moderate given their age group, we got a little more than 35%. So my probabilities are different. So these are not independent events. If I got the same probability, they would be independent.